Alright, so today what I'm going to do is I'm going to do an introduction to acid-base titration curves. So you have to be familiar with the different types of titration curves and some of the features that allow you to figure out what kind of titration is. First off, strong acid, strong base titration means we got OH minus and H plus. In this case, it tells us on the bottom what we're adding. We're adding a base. We're starting with an acid. How do we know? Well, look at the pH. Look where the pH starts. If you have a strong acid, the pH is going to be less than 2. So if it's a strong acid titration, notice where the pH starts, and you notice that the line kind of slopes, gradually slopes, and then eventually you reach equivalence point. There's two ways you know that this is a strong acid, strong base titration. The fact that the pH is 7, because at 7, or at equivalence basically, the only thing you have left is water. So if you just have water, the pH of water is going to be 7, and that's a strong acid, strong base titration. So the fact that the equivalence point is 7, and the fact that the pH of the acid starts very low, less than 2, that's how I know this is a strong acid, strong base titration. All right? Next, here's a typical titration curve, strong acid, strong base. Again, pH is 7. When I go to select an indicator, what am I thinking about? Well, when you go to select an indicator, what you should do is you should focus on an indicator that's going to change color after equivalence. That's why if you notice here, methyl red, which changes color from about a pH of 4 something to 6 something, would not be a great choice for an indicator because the color change would occur before equivalence. So ultimately, we always use phenolphthalein in a strong acid, strong base titration because phenolphthalein changes color after the pH, after equivalence, after 7, slightly after you get the color change right there. So that's key when we're talking about picking an indicator. Here's a strong acid, strong base titration curve yet again. They're showing you here's methyl violet, phenol blue, bronthymol blue, phenolphthalein, and now xeron yellow. So you have all the different indicators. So really you would not use that as an indicator, that as an indicator. That's close. The color change is close to equivalence because equivalence is right here. But it might be only a slight difference in color, so it might be hard to tell the color difference. So ideally phenolphthalein is the closest one that has a pretty distinct color change, and then this would be kind of too far after. And then general shape of a titration curve, remember the top of a titration curve is you have excess base producing that, so you have a high pH. Equivalence point is going to be 7. You're going to have a very low pH when you have a strong acid, strong base, and that's the key things you can see when it starts out to identify it. Well, what are we going to compare and contrast that to? A weak acid, strong base titration. If you're titrating a weak acid, you're taking basically like acetic acid with NaOH, which is basically going to be OH minus. You're going to be left with this salt at equivalence. Once you get to the equivalence point, you're going to have this left over besides water. That's your other product. We know a negative ion acts as a base. Any negative ion is going to act as a base by ripping an H off water, producing OH minus. So what does that mean? At equivalence of a strong base, weak acid titration, anytime you have a weak acid or a weak base, the equivalence point can't be 7. In this case, the equivalence point is always going to be greater than 7 when you're titrating a weak acid. How do I identify this as a weak acid titration curve? Notice the initial pH is above 2, and then you have a gradual little slope here. This area represents the buffering area, where you have a buffer system basically buffering against the changes in pH. It's a natural buffering area, and then finally the equivalence point is above 7, identifies it as a weak acid titration as well. The rest of the curve from equivalence point looks very, very similar to a strong acid, strong base titration. If we take a look at it, we're trying to find a indicator. Again, we're going to pick phenolphthalein. Why? Well, if we look at our equivalence points here, and we'll get a nice color change within the band of that. So we use a pKa actually. We take the pKa value of an indicator to pick what we're going to use in our titration. Notice I can read on the bottom of it. I know exactly the volume at equivalence. Equivalence in this case, the volume, it would take 20 milliliters of NaOH to reach equivalence. And my pH at equivalence is going to be somewhere around 9.0 reading off the chart. So those are two key things we can read off the graph. Another thing I need to be aware of is halfway to equivalence. If equivalence is 20, that means at 10, pH equals pKa. And you need to be able to identify that on the graph as well. Two key things that allow me to identify this as a weak acid titration. Equivalence point is above 7. Second thing is, look where my value is. I have a pH that's going to be above 2.0, and it's a gradual slope up this way, identifies it as a weak acid titration. If you look here, key thing to know is the buffer region is when you have the acid and its conjugate base buffering. That's going to be the zone. That's why the slope of this line in a titration curve is very, very gradually uphill, even though you're adding a strong base. Is because what's happening is you have a buffer system that's working in between the line here and the line here. So that's where you have HA and A minus present. Before you start over here, you're really just going to have HA. Then when we talk about equivalence, the equivalence point here is 25. How do I know? Because that's basically where equivalence is reached. If I drop all the way down, 25 milliliters is going to be the equivalence point. The only thing left is going to be my conjugate base, or my A minus at that point. Then after that, the thing that's really going to set the pH is the OH that I'm dumping in. So when you look at a titration curve, it helps if you kind of understand what's happening in each region. Now, key things. You have to know halfway to equivalence, pH is equal to pKa. So for example, if 10 is my equivalence point, 5, I would know pH is equal to pKa 4.75. I know it's starting at a pH above 2, so it's a weak acid. I also know that the equivalence point is above 7. So that's how I identify a weak acid. If I compared the two, just the two general outlines of a titration curve, I know this is a weak acid. Starting point, you got a buffering region occurs right there, and my equivalence point is going to be pretty high as far as pH. Strong acid, I start out low. My equivalence point, if I trace it over here, is going to be right around 7. So those are some key things to keep in mind. Now, the other thing we can do is if we compare the buffer region, this represents a buffer region, and you need to be aware of that. I know I highlighted on the other slide. But when you go to pick an indicator, again, if the equivalence point, here's my equivalence point for the weak, my equivalence point for the strong acid, strong base titration would be there. Methyl red would be an inappropriate indicator to use because a color change is occurring before the equivalence point. So you want to really, really pay attention to that when you're picking your indicator for your solution. Now, the other type of titration that doesn't get as much press is strong acid. If I took H plus and a weak base, what's happening is the H is going to come over here, creating basically NH4 plus, a positive ion. At equivalence, a positive ion will give an H to water, thereby creating H3O plus or H plus, which means anytime you titrate a weak base, the pH at equivalence is going to be below 7. Always. Because you're going to leave a positive ion afterwards, and we know from before a positive ion always reacts to produce a acidic solution. So if you look at this, notice it's a weak base. Look at the pH starts at less than 12, so you can tell that it's a weak base. You got a nice little slope there because this is the buffering zone in a weak base titration. And then notice my equivalence point is about 5.25. So I know my equivalence point is below 7. That's how I can identify that this is a weak base titration curve. A couple other things. Here's the buffer region highlighted again. You have the pH at equivalence point would be 5.27. So then using the pKa, an ideal solution for this would be methyl red, because the pKa for methyl red, if you look it up, is very close to the pH at equivalence of 5.27, and that's how you would justify it. If you notice equivalence, I can drop down. The equivalence point is 40. Halfway to equivalence, in this case, POH is going to be equal to PKB. If you want to convert it to pH, you could just subtract it from 14. So you could take the PKB for NH3. You know that your POH subtracted from 14, and you would have your pH. Other thing you need to be aware of is when you pick an indicator, we use the pKa value. So typically what they would do is, if you look on that last, imagine they gave you this titration. They said, well, you have to pick an indicator. And you calculate the pH at equivalence is 5.27. That's my pH at equivalence. One of the things they will ask you to do on the AP exam is they will give you a chart, and they'll say, would you use methyl red, bronthymol blue, or phenolphthalein? You would say, I would use methyl red because it has a pKa of 5.5, closest to the pH at equivalence. It would give you my best color change. It would function as the best indicator. And in the course of the question, you'd be sure and answer that the pKa is closest to the pH at equivalence. That's a key thing. Last thing is, it comes into play not very often on the AP exam, but you should be aware of it. Polyprotic acid means it has more than one H. So example would be H2SO3. If you're titrating H2SO3, it means you titrate the first H. So you go from H2SO3 to HSO3 minus. that pH at equivalence would be here. So you basically end up with 2 areas of titration. You have 2 equivalence points. You have 2 equivalence points in a polyprotic acid titration curve. You don't need, for our purpose of the AP exams, to be able to calculate this out or measure this, but you should be able to recognize a polyprotic acid titration curve when you're looking at it. Key thing, if you look, is you have a buffer region on both of these. Since we're dealing with a weak acid, you have 2 buffer regions and 2 equivalence points. That's the only other thing you want to pay attention to. Make sure you review this material because I will be quizzing you on it when you step into class tomorrow. Hopefully you had a nice 4-day weekend, and this week's going to be a very rigorous week, so make sure you're studying, preparing, and getting ready. All right? Have a nice rest of your day.